Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class, and I'm putting it online in case it would be helpful to others as well. This is the third video in our first cluster of sections on applications of derivatives where we discuss curve sketching. There is a link to a printable set of guided notes that you can use to follow along with the examples in this video in the description of the first video for this section. All right, so we only have a little bit more to do in our notes, and we're going to pick up here with examples 6 and 7. And what you're going to see in these last few examples is that we're going to need to reference a couple of the theorems and other information that we discussed in the first video. The directions for example 6, well, the question, I guess, is what are the absolute extrema of y equals e to the x squared on the interval from -2 to 2? So what we need to reference that we talked about in the first video, okay, let's see if I can hit it right on the first time. I want to say it's this one. No, darn it. It's back here. It's in the theorems. Okay, here it is. We need to reference the extreme value theorem. The extreme value theorem says that if a function is continuous and on a closed interval, then you can identify both a maximum value and a minimum value over the interval for the function. The reason that I definitely know for sure that we're going to reference this theorem in example 6 is because it asked us for absolute extrema. And we were given a closed interval for our function. Okay, so going back to example 6, what we need to be able to do to find extrema is what we've been doing. Take our first derivative, set it equal to 0 or find where it does not exist to identify critical points, and then test those critical points to determine if they're maxes or mins. However, the test that we're going to do whenever we are looking for absolute extrema looks a little bit different than the test that we did to find relative extrema when we were sketching our curves. Okay, but before we do that, let's not get too ahead of ourselves here. Let's start with our derivative. E is easy, right? The derivative of e is itself, but don't forget about chain rule. The derivative of x squared is 2x. Okay, now let's set that equal to 0, and we have two factors here. We have an e to the x squared factor to be set equal to 0, and we have a 2x factor to be set equal to 0. Solving each of these will give us our critical points. Now, e to the x squared can't be 0, right? We've already discussed that. E is a positive number being raised to a power. Whatever you have in here is not going to result in a negative number or 0. So all we have to do is solve this little equation, and that gives us x equals 0 as our critical point. Now, if we're trying to find extrema, that's where we start. We start with critical points, right? But keep in mind, and this is going to reference something that we talked about way back at the beginning, extrema can also occur at endpoints. And so even though we only have one critical point in example 6, we still are going to be able to find an absolute minimum and an absolute maximum because, again, we also have endpoints. And the test that we use whenever we are looking at endpoints is called a candidates test. Okay, and that candidates test says you should be able to take all of your candidates. In this case, it would be the endpoints, -2 and 2, and the critical point 0, and look at the function values at those candidates to determine where is your absolute max and where is your absolute min. And again, because this is a continuous function on a closed interval, the extreme value theorem applies, and that means we definitely should be able to find both an absolute min and an absolute max. Okay, so what do we do from here? Well, look at what this column is labeled. It's labeled y. So we are going to take these x coordinates and put them back into the original function. Okay, like this. -2 squared is 4. And so the value I have here is e to the 4th power. Okay, I'm not going to grab a calculator and approximate what that is. E to the fourth power is good enough. Next, for x equals 0, 0 squared is 0, and e to the 0 is 1. Finally, filling 2 in for x, 2 squared is 4, and so we have another e to the fourth as our value for the other endpoint. Okay, so what does this mean? This means that I see two absolute maximums. Do you agree? E to the fourth power is definitely a higher y-coordinate than 1. So if you think about it, doing a real quick rough sketch of what this graph could look like, it doesn't matter how well you approximate e to the fourth. It's just definitely a positive number, first of all, and it's bigger than 1. You have 0, 1, and then you have 2 at e to the fourth. And so, you have something like this. We didn't test concavity or anything, but we have something that decreases and increases. So these are our absolute maximums. And this is our absolute min. Now, if this was an AP problem, we should get a little bit more technical about how we write our answer out, and we will talk about that in class much later on. Okay, let's just do the basics right now. Candidate test, find your candidates. Those are your critical points and your endpoints. Find their y-coordinates. The highest y-coordinates of them all are the absolute maxes. The lowest y-coordinates of them all are the absolute mins. Let's try another one. Example 7. Let me grab a different color. What are the absolute extrema of y equals negative x cubed plus 3x squared on the interval from negative 1 to 4? Okay, once again, I am given a continuous function on a closed interval. So that means EVT applies. The extreme value theorem applies. I should be able to definitely find an absolute max and an absolute min. How do I do that? I take the derivative. Negative 3x squared plus 6x. I set it equal to 0, or, if possible, find where it is undefined to get our critical points. Here I could factor out a negative 3x. And what am I left with? X minus 2. Set that equal to 0. Set that equal to 0. And we get x equals 0, x equals 2 are our critical points. So there's 2 candidates for maxes and mins. Where are the other ones? Our endpoints, right? So let's take all 4 candidates this time. Left endpoint, critical points in between, and right endpoint. And we will find their y-coordinates to determine, where's the absolute max and where's the absolute min. Okay, so I paused the video to fill in my y-coordinates just to try to save a little bit of time because I know all these videos are so long. All right, again, what I did here was I just filled each x-coordinate into the function to get its y-coordinate. Now, what are we looking for? We're looking for what is the lowest point of them all. Let's start there. What's the lowest y-coordinate of them all? It's definitely negative 16, right? So this function has an absolute minimum value of negative 16 at x equals 4. But for now, we'll write that out if this was like AP practice. But for now, we'll just circle it and say there is our absolute min. What's the highest y-coordinate of them all? There's 2 of them, right? Y equals 4 is the highest value we see, and it happens twice at x equals negative 1 and at x equals 2. So there's our absolute maxes. Okay, so that was just a little bit of practice with finding absolute extrema, where you apply the extreme value theorem. Next, let's talk about MVT, the mean value theorem. Notice that this time the example specifically references that theorem. Does each function satisfy the hypotheses of the mean value theorem on the given interval? If the hypotheses are satisfied, apply the conclusion and solve. Okay, so this is just some basic problems to help us ease into mean value theorem. We will definitely look at this again, in our AP practice and actually in the next chapter as well. But we're going to start with some simple ones here because we're still trying to get used to what are the hypotheses and conclusion of the mean value theorem. Yes, I hit it the first time this time. Okay, so the mean value theorem says that you have a continuous function on a closed interval and the function is differentiable on the open interval. So we don't need to worry about differentiability at the endpoints, but it needs to be differentiable at any point on the interior of the interval. If you have those hypotheses satisfied, then it says that there exists some x coordinate in the interval given to you such that the derivative value at that x coordinate is the same as the average rate of change of the endpoints. Okay, now that's all like a really fancy way of saying that if you have these hypotheses satisfied, then there is a point where the slope of the tangent line is equal to the slope of the secant line between the two endpoints. Okay, that's what that's saying. So we'll come back and look at these words again, but let's just start with the hypotheses. Do we have a continuous function on a closed interval and it's differentiable in the interior of that interval? Let's check it out. Going back to example 8a, we have the function x squared, and x squared is continuous everywhere, right? And it is differentiable everywhere. So yay, we have the hypothesis satisfied. By the way, how do you know that it's differentiable everywhere? Well, first of all, I know that y equals x squared is a smooth curve with no corners, cusps, vertical tangents, or discontinuities. Also, I know the derivative, is 2x, and that has no restrictions. So that's how you definitely know that it is differentiable everywhere. Okay, so the hypotheses are satisfied. Let's just start by saying yes, MVT, the mean value theorem, applies. Now, if it applies, you should be able to apply the conclusion. So let's go back and look at that conclusion again. The conclusion of the mean value theorem says you should be able to find a number somewhere in that interval given to you where the derivative value of the function at that number is equal to the slope of the endpoints. Okay, the slope of the secant line, I like to say. How are we going to find that? Well, actually, you can set it up pretty easily. I think first of all, let me just write the formula over here. What we're trying to do is find a C such that f prime of C is equal to f of B minus f of A over B minus A. But this, again, is just saying the slope between these 2 points. So let's set these up as ordered pairs. When x is 0, 0 squared is 0. And when x is 2, 2 squared is 4. The slope between those 2 points is 4 minus 0 over 2 minus 0, which is 2. Okay, so if we, I'm going to draw a little picture too, a little graph. So bad. Okay, 0, 0, 1, 2, 1, 2, 3, 4. We have a little portion of our parabola here. And the slope between these 2 points, I'll try to draw that in a different color. The slope of this secant line, that's supposed to be a line. Trying to make it straight. The slope of that secant line is 2. That's what we found right here. Okay? Now, somewhere else in this interval, we should have a point where the derivative value, or the slope of the tangent line, is 2. Okay, how do we find it? Well, pretty easily, actually. For this one, you take your derivative. It's 2x, right? And let's write it in terms of c. If f prime of x is 2x, then f prime of c is 2c. Now, take that 2c and set it equal to what you found to be your slope of your secant line. Solve. Divide both sides by 2, c equals 1. Now, what is that saying? That's our answer, by the way. It's saying that if we look at this point on the curve, which is 1, 1, and we draw a tangent line to the curve at that point, it's parallel to the secant line that we drew between the endpoints. The slope is the same. Yay, and that's the mean value theorem in a really simple example. And it might not seem like much right now, but as we continue to talk about the mean value theorem, I think you'll find that it's pretty powerful in calculus. Okay, but again, we're just getting a start to it today with some simple examples. Now, let's take a look at example 8b. We have the function, the absolute value of x on the interval from -1 to 1. Okay, does this function satisfy the hypotheses of the mean value theorem? Well, one more time, going back to the mean value theorem. Remember that it said you had to have a continuous function on a closed interval. We have that actually. The absolute value of x is continuous, right? No restrictions, and it was given to us on an interval from -1 to 1. But the mean value theorem also says that the function has to be differentiable everywhere inside of that interval. Think about the absolute value of x. It is not differentiable where? It's a corner, right? It has a corner. It has two lines that come together at x equals 0. Not differentiable at x equals 0. So MVT fails here, or we could say MVT does not apply. Probably like those ones because you don't have to go any further. That's it. That's the answer. All right. Finally, the last example, I can't wait for this one. The last example that you're going to see is one that references one of the other pieces of information that we talked about in the first video. Okay, the question is, what is the function with each given derivative? And notice that you have 4 different parts to answer here. Okay, so what you're given is the derivative, and you are trying to find the original function, the function that when you take the derivative, you get that. Okay, so what this is referencing, and I'm trying to remember where it was that we talked about this. Nope. There it is. I put it in pink. I knew I put it in a color. Okay, it's referencing the antiderivative. We're trying to find the antiderivative. Okay, so I don't know if you remember having this discussion in the first video or not because that video was so long, but we had some corollaries from our mean value theorem that led up to this pink definition. A function, capital F of x, is an antiderivative of a function f of x if f prime of x equals f of x for all x in the domain of f. Now, something that you need to keep in mind, however, is this little piece of information right here. If you can come up with a function, keep in mind that you can also come up with another function that differs by a constant. Okay, and we call that constant plus c. So what I mean by that, we have a really easy example to start us off, is I think we know that the function that has a derivative of 2x is x squared, right? Y equals x squared. But really, it could be y equals x squared plus 3, or y equals x squared minus 5, because the derivative of the constant goes to 0, right? And so you don't see that part in your derivative equation here. So what we say is y equals x squared plus c is the antiderivative of 2x, and that covers all possible functions, because of the possibility of there being a constant. Okay, let's try another one. If the derivative is sine, f prime of x is sine x, then what is the original function f of x? Well, we know that sine and cosine are related in their derivatives, right? And I honestly always have to go back to like how I learned it when I learned the derivatives. The derivative of sine is cosine. the derivative of cosine is negative sine. Okay, meaning if I say the function is cosine, that derivative is negative sine. However, I don't see a negative sign here. I see a positive sign. So I have to move that negative up here. The original function is negative cosine. That would get you a derivative that is sine. And don't forget the plus c. It could be negative cosine plus 2. It could be negative cosine minus 11. It could be negative cosine plus pi. Any constant would not show up in the derivative because it goes to 0. Okay, so we had a couple of fairly easy ones, and now these ones get a little bit trickier. Here we have the derivative 1 over x cubed, which we are going to rewrite, this is still g prime, as x to the negative third power. All right, what do we do here? Well, we need a power function, right? We need something for our g of x function that is x to a power. And when we apply power rule, we end up with this. So power rule is the power goes down by 1, right? So what power goes down by 1? To negative 3. Sorry, I didn't finish I was writing. What power, when you take away 1, gives you negative 3? That would be negative 2. Does that make sense? Negative 2 minus 1 would give you a negative 3 power. Okay, however, don't forget about the first part of the power rule. That power comes down in front. So what I'm saying is if we think that our function is x to the negative 2, that derivative is negative 2x to the negative 3. Okay, we don't see a negative 2 as a coefficient here. So what do we do about that? Well, we compensate for it with a constant multiple here of negative 1/2. If we take negative 1/2 times this negative 2, it goes to 1, which is what we want right there. Don't forget the plus c, and there's your answer. I forgot to box this one. All right, finally, last one, part D. Y prime is 1 over x. You may want to start by rewriting it like we did this one as x to the negative 1. Okay, but there's a little bit of an issue this time. If we think about what number, when you subtract 1, results in negative 1, that number is 0. And we can't have x to a 0 power. You can't do it like this one. You can't say, oh, well, it's x to the 0. That doesn't work. Okay, so what do we do about this one? This one's a special function, so you sort of have to just remember it or look it up. The antiderivative, or the function that when you take its derivative is 1 over x, is the ln of x plus c. Okay, so finally we are finished with these notes, and we've seen everything that we needed to see for our first cluster of sections for chapter 4. Which is all about curve sketching, but also, as you can see, some other fun little bits that are previews to things that you are going to see in later chapters. As usual, I hope this was helpful. Bye.